Hello, I am Stephen Ayoub, and I am an undergraduate physics major working with Dr. David Wexler and Dr. Paul Song at the Space Science Lab. The surface of the Sun is the photosphere, where most of the energy that reaches Earth is from, and what you see with the naked eye. The chromosphere is this darker red and orange layer just above the photosphere, and is partially ionized. At the top of the chromosphere is a relatively thin transition region, where the gas becomes fully ionized and behaves very differently as you go farther out into the corona. The transition region and corona have temperatures hundreds of times greater than the photosphere and chromosphere below, a problem that is still not fully understood after 80 years. As part of ongoing research at the Space Science Lab, I have developed a simple but effective model for the chromosphere based on hydrostatic equilibrium. Like in the atmosphere, there is a pressure gradient on the Sun, so this is important for the chromosphere as ionization changes with pressure. Hydrostatic equilibrium is just the force balance of pressure and gravity. This is what you might see in a fluid dynamics class, but the chromosphere is ionized, so we define the ionization fraction alpha, which goes from 0 to 1, and we really have to take into account that we have three species of particles: positive ions, electrons, and neutral atoms. The ideal gas equations are missing these here because the n's are actually numbered densities, particles per volume. We have our differential equation, and now we just need to choose two functions and solve for the third. Luckily, the conditions for the Saha equation are met, and shown here is the formulation used in the model. The temperature model can be isothermal or empirical. Putting this all together is a bit of a mess, but it's still just an ordinary differential equation, so numerical methods like Runge-Kutta are perfect for this. While the pressure and number density plots are important because they do vary from the standard hydrostatic solution, which is just an exponential, the ionization or alpha plots are also of note. We say that the transition region begins at the point where alpha turns to 0.5, where the more fluid acting chromosphere becomes a much more highly ionized plasma. Currently accepted values range between 2,000 and 2,200 kilometers. For example, average has it at about 2150. And the determined value from our results are actually fairly in concert with that. The conclusions here just reinforce the idea that gravitational stratification and partial ionization have a large role in the chromosphere's formation and structuring, as well as the transition region and corona to some extent. But this is still a work in progress. We're continuing to add magnetic field effects to this model, as well as hoping to extend it to a true multi-fluid model, where we solve the fluid equations for each species of particles individually. But I'm happy to hear questions. Thank you very much.